All right, good morning, everyone. Few things before we get into today's topics. First of all, on the midterm, I know the average was lower than the previous midterm. For whatever it's worth, I'm not too bothered by that. I expected the average to be lower because the previous midterm had a really high average. I'm not looking to decimate the class over this. We've already done some triaging into the alternative path. I feel like, people have already triaged into where they need to be, and I'm not going to punish anyone for being where they need to be. The question came up, is the final cumulative? A little bit. I mean, there will be some Fourier stuff on there. There will also be some Legendre polynomials and some Bessel function stuff, but it'll be.
Did you see my earbuds?
Someone say something? Okay, that's my device. The final will be weighted towards the later stuff because the later stuff builds on the earlier stuff. But I'm really not looking to decimate people. I wouldn't worry if you're anywhere near the median on this one. I wouldn't worry too much. Of course, some people did much better or much worse, but I don't think that the median student here needs to worry. I'm not looking to decimate the class over this. Any questions?
I just hopped in the meeting. Did you just announce the median for the past midterm and the mean?
65.
Okay.
I also posted it on Blackboard.
Got it.
Question in the chat will be like 25, 30, where there's a question from each exam, and then the rest is based on the last problem sets. Probably more or less like that. It'll probably be the same length as the midterms because the final exam time period is only 2 hours. The official time period, I'm going to give you a couple hours before and after that, since I know my exams take a little more than 2 hours and some people might have a final before or after that. If you have 3 in a row that day, then talk to me. But if you don't have 3 in a row that day, then I'm going to probably allow 5 or 6 hours for it so that everybody's got some flexibility. All right, with that, let's talk about Legendre polynomials. I introduced Legendre polynomials by fiat before. I just said, okay, here are some polynomials. And they have this interesting property that the integral from -1 to 1 of PL of x, PK of x, dx is equal to 0 if L is not equal to K. We just asserted that. Well, we asserted that these are the polynomials, and then we found that if we plugged in if we plugged them into that integral, we got that property for them. Now I want to show where these particular polynomials come from. And for that, we have to start with the Laplacian operator, del squared f, which is partial squared f, partial x squared, plus the second derivative with respect to y, plus the second derivative with respect to z. And this shows up all over the place in physics. The wave equation, Laplace's equation, diffusion equation, Schrodinger. Technically, Maxwell's equations don't quite reduce to the wave equation. They reduce to something that's slightly more complicated because of the vector boundary conditions, but it still shows up there in anything that Maxwell's equations reduce to. So it shows up all over the place in physics. We spend a lot of time solving it. But we don't always solve it in Cartesian coordinates. Oftentimes we solve it in spherical coordinates because maybe you've got electrons in an atom and you want to understand how the solutions to the wave equation look if the electrons are in a spherically symmetric potential, or we scatter light off of a spherical particle. And it's an interesting fact of the universe that while there is no such thing as a perfect sphere, a whole lot of particles are so close to spherical that we can model them as perfect spheres. And then their optical properties are important. They're important for understanding the atmosphere. They're important for understanding clouds of dust in outer space. They're important in biology because we can often model particles in biology as spherical and study the scattering of light from them and understand why light behaves the way that it does in tissues. So we solve these spherically symmetric. Oh, here's another example. The Earth, a layered sphere. Okay, now, yes, there are inhomogeneities, but still, it's a fairly layered sphere, and the propagation of seismic waves through that spherical medium is really, really important. It's the propagation of spherical waves through that spherical medium. It's the propagation of seismic waves through that spherical medium that lets us know that the center of the Earth is layered. It lets us know when someone sets off a nuclear bomb and does an unsanctioned nuclear weapons test. So solving the wave equation in spherical media matters a lot. Question came up, why are particles mostly spheres? The short answer is that when particles of liquid are condensing, a sphere has the minimum possible surface area. And since liquids prefer to be in contact with themselves rather than air, they will try to take on a shape that is very close to spherical. It's why the planets are spheres, more or less, because originally the planets were not solids, they were balls of gas and dust, and then they became, as they cooled, they became liquid-like. And again, minimizing the potential energy, minimizing the surface area, keeping the liquids in contact with themselves rather than vacuum, minimizing the gravitational potential energy. All of these factors came into play. And so things take on naturally spherical or nearly spherical shapes. Okay, so the universe has spheres and we want to solve the wave equation for spherical situations. Well, it turns out that del squared F is equal to 1 over R squared, partial by partial R, R squared, partial F, partial R, plus 1 over R squared sine theta, partial by partial theta, sine theta, partial F, partial theta, plus 1 over R squared sine squared theta, partial squared F, partial phi squared. Why it takes on this form? There's no simple answer. It's a very tedious thing that you could work through. They do work through it in chapter 10. The answer they get is this. And normally physicists like to answer why questions, but the thing is that this is one of those why questions that unless you spend a lot of time working in weird coordinate systems, you'll answer this why question exactly once in your life. To get the form, well, twice. Once to get the form of the Laplacian operator in cylindrical coordinates, and then to go to the harder problem of getting it in spherical coordinates, and then for the remainder of your life, even if you're doing pretty hardcore quantitative things in physics, you will simply use it. You will never again derive that. If you do work in a field where you work in lots of different coordinate systems, then you can go read section 10 point whatever of the book, master those techniques, derive it in umpteen million different coordinate systems. The fact is that it does take this form. And this certainly looks messy. It is messy, but it's still better than Cartesian if we have a spherical problem, because for starters, sometimes all of these derivatives are zero and we just have this. Other times, these derivatives aren't zero, but they give rise to formulas that have geometries or shapes that we would recognize. For instance, if some of these derivatives are non-zero, you can get things that look like electric dipole fields. You know how if you've got an electric dipole, so you've got a negative charge and a positive charge, and there's a little dipole moment, then the field circulates around it. All right, well, here you've got a field that's decaying as you get farther away, but it also has a weird spiraling shape that depends on this angle theta, okay? And then there are more elaborate forms. There are things called quadrupoles, octupoles that involve more and more elaborate functions of theta. But we can classify things like that. And you'll spend a bunch of time doing that in E&M next semester or next year. Maybe in chemistry, you remember orbitals. And they said that there are s orbitals, which are spherical. And then there are p orbitals, which look like dumbbells, and they get 3 different orientations. And then there are d orbitals that I can't draw. Those things come from these kinds of solutions to the wave equation. And if I share my other screen, we're going to be learning this week about functions called spherical harmonics. And these spherical harmonics have 2 numbers associated with them, indices, L and M. And for different values of L and M, we can get, say, here's a p orbital. This is an s orbital. The distance from the origin is the value of the function. Here's a p orbital. Again, the distance from the origin is the value of the function. So when we're out, this is a plot in polar coordinates. When we're out in the equatorial plane, everything just goes in to the center. This is a p orbital. This is one of the d orbitals. This is one of the f orbitals. We can take linear combinations of them. For instance, here's a case where I take a linear combination of 2 of them and I get something oriented this way. I'm going to change how I add them, and I change the orientation of the orbital. So that's where these things show up. You have seen in chemistry classifications. They didn't say, oh, we're classifying solutions to the angular part of the wave equation. They just said the electrons are in these different kinds of orbitals. Well, the electrons obey a wave equation. And if they obey a wave equation, then they're concentrated in places of high wave intensity. And the places of high wave intensity have shapes like that. I don't claim that any of this is intuitively obvious, but I'm saying that we're going to be studying the functions that give rise to these graphs. Any questions so far? All right, so we need to solve the wave equation. We are going to assume solutions to the wave equation that are factorizable, meaning that there is a function of r times a function of theta times a function of phi. Now, these subscripts are not vector component indices. F sub r does not mean a radial component. It just means that phi is a product, F is a product of 3 factors. One of those factors only depends on r, one only depends on theta, and one only depends on phi. You may be thinking, well, come on, there must be more solutions than that. Those can't be the only solutions to the wave equation. Others are thinking, oh, okay, I learned those are the only solutions to the wave equation. Well, the fact is that I can take combinations of these. You could think of these as the chemical elements that I'm breaking it down to. And then I could take different combinations of these. So like I could take FR1 of R times F theta 3 of theta times F phi negative 17. Well, actually, the way we normally index these, that would be 17 and that would be negative 3. And I could add to that FR4 times F theta 5 times F phi negative 2, whatever. I could take all these different combinations of solutions to the wave equation. And these would also be valid solutions to the wave equation. So factoring it is basically the simplest possible way to write down a solution. Factoring it means we've got something that only depends, or we only really have to worry about this, something where we only have to worry about this, and something where we only have to worry about this. Those are the simplest possible ways of solving the wave equation. And then any more complicated solution comes from adding those up. It's the thing we've been doing with Fourier series. You know, if you think about it, sinusoids are solutions to the wave equation. And we took possibly very complicated oscillating waveforms and said, we're going to break them up into simpler sinusoids. Well, now we're taking different solutions to different parts of the wave equation in spherical coordinates, and we're going to add them together, multiply them together, and then add up what we get from that. The only way this works is if this combination of derivatives acting on F gives me back some constant times F. And this combination of derivatives acting on F gives me another constant times F. And this combination acting on F gives me yet another constant times F. So we're looking for eigenfunctions of these derivative operators, of these differential operators. These derivatives commute with each other, all right? It doesn't matter what order, whether we, because the derivative with respect to R doesn't care about factors of phi or theta, that means that these derivatives with respect to R commute with these derivatives with respect to theta and phi. And whenever two matrices commute with each other, you're thinking, well, these aren't matrices, but I'm making an analogy right now. When two matrices commute with each other, they can have simultaneous eigenvectors. Likewise, when two differential operators commute with each other, they can have simultaneous eigenfunctions. We've already seen eigenfunctions. E to the I phi is an eigenfunction of the derivative operator because partial by partial phi, e to the I phi, is equal to I e to the I phi, which is a constant times our original function. Right? And there are many of these. I could write down e to the I m phi, then partial by partial phi e to the I m phi would be I m e to the I m phi. Again, another constant times the original function. These are the simplest possible solutions. Eigenfunctions are the simplest possible solutions to these differential equations. but we can take these eigenfunctions and make anything else out of them, just like we can take the chemical elements and make any molecule out of them. So this week we're going to talk about these two parts of the wave equation. This part we're going to say very little about, right? Let's start with the with 1 over r squared sine squared theta this has to be equal to constant times f phi, constant over r squared sine squared theta, right? Has to be equal to that. Whenever we take the derivatives, we should get back the original function, and then this multiplication comes after taking the derivatives. Well, as far as I know, all of the eigenfunctions of the second derivative operator can be written as e to the I m phi Now, you're probably assuming that m is an integer because, well, we almost always use m to represent an integer unless we're talking about mass. M can basically mean m can mean a lot of things in physics. But when we're doing purely mathematical stuff, m is almost always an integer unless m is a mass, but that's not purely mathematical. And then sometimes m could be a magnetization. But I want to argue, I'm not just assuming that m is an integer. I'm not just making that assumption arbitrarily, pulling it out of nowhere. M has to be an integer for the simple reason that in spherical coordinates, say I'm over here. Okay, so here's my z-axis, here's my theta, here's phi. Well, if I go around, if I go to phi plus 2 pi, I've just returned to the original point, right? I'd better, because I'm back at my same point, f had better be the same. I better not change anything going around 360 degrees. If I change things going around 360 degrees, then there's something very wrong. And there's a tiny exception for quantum spin, but quantum spin is weird. So my answer to that is the same answer that your parents gave when you asked uncomfortable questions as a kid. Ask me again when you're older. All right, but other than that one tiny exception for quantum spin, we had better get the same thing back when we go around by 360 degrees, which means e to the I m phi had better be equal to e to the I m phi plus 2 pi equals e to the I m phi e to the I m times 2 pi, which only works if 2 pi m is an integer times 2 pi. So m must indeed be an integer. Any questions on that? All right, good news. We just solved 1/3 of the wave equation. Bad news, we just solved the easiest third of the wave equation. We still have the 2 harder thirds to solve. Next part, we've got 1 over r squared sine theta, partial by partial theta, sine theta, partial f by partial theta. And that has to be 1 over r squared times c times f theta of theta, where c is some unknown constant. we'll eventually learn that it's an integer times that same integer plus 1. And it will come from the requirement that, well, we'd be able to write down a nice sensible function that's well-defined and well-behaved, just like our e to the I m phi condition. But we're not there yet. For now, it's just a constant. The math doesn't care. If all I say is, hey, I've got a variable, I'm naming it theta, and I'm not assuming that this theta is an angle, I'm not assuming that anything must be well-defined for all values of theta. I'm just saying, I've got a differential equation. I gave that variable the name theta because its grandfather's name was theta and I wanted to honor him, all right? I gave it the name theta because it sounded like a pretty name, so let's name it theta. And we solved a differential equation and we wrote down an expression. Mathematicians could do that. If this weren't a physics class, we didn't have to care about whether things match up with reality. We could just say, hey, here's an equation. It's this. Looks kind of weird, but you know, an equation is an equation. We solve it. We got this constant. Matching things up with physical reality is where the constant will eventually get the value integer times integer plus 1. First thing I'm going to do is cancel out the r squared that's on both sides. The r squared tweeted something terrible, so it goes. Next, we're going to make a change of variables. Why are we going to make a change of variables? There's no a priori reason I could give you why it should be in any way obvious that we must make a change of variables. Okay, it just happens through trial and error and experience that people learned that if we make this change of variables, things work out better. So I'm going to say that x is equal to cosine theta. And I had you work through this on today's assignment, so I'll just review it quickly. You should have found that partial f partial x is equal to partial f partial, sorry, other way around. Partial f partial theta is equal to partial f partial x partial theta. And what's the derivative of x with respect to theta?
0.
Oh, the derivative of cosine theta with respect to theta is 0?
Minus sine theta.
Yep. So that's good. Now we have got that this is minus sine squared theta partial f partial x. And then meanwhile, 1 over sine theta partial f partial theta. Remember, partial f by partial theta was sine theta times partial f partial x. So if I divide both sides by sine theta, I'm going to get minus partial f partial x. So this thing up here must be minus partial by partial x. So we've got the derivative with respect to x of minus sine squared theta, or minus the derivative with respect to x, of minus sine squared theta partial f by partial x. All of that is equal to a constant times f. These go away, the signs cancel out. Well, now we've still got this sine squared theta when we wanted things in terms of our variable x equals cosine theta. Any ideas how to write sine squared theta in terms of x?
Just use the sine squared theta plus cosine squared theta equals 1 identity.
Yep. This is 1 minus cosine squared theta, or, oops. What did I just do?
You
Screen share is gone.
stop sharing your screen.
Yeah, now I'm trying to get back to my main screen so that I can reactivate sharing. Okay. All right. So we put all this together and we've got that partial by partial x of 1 minus x squared partial f partial x equals CF. This form of the equation is worth holding on to for what we're going to do later, but it's also worth rewriting this using the product rule. We're going to get 1 minus x squared times the second derivative of f minus 2x times the first derivative of f, because this is just this thing here, minus 2x, is just the derivative of 1 minus x squared. Any questions so far? What I want you to take away is that we started with the wave equation and we decided that we're going to factor out our solutions, and we decided to work on this term, right? We're looking for simple solutions because we can always build more complicated solutions by putting together simple solutions. Again, it's very much like chemistry. You can build more complicated matter by combining the simplest building blocks of matter. We can build more complicated solutions to the wave equation by assembling the simplest solutions to the wave equation. And then we did some changes of variables and we got this differential equation. This differential equation doesn't look much like the wave equation, but this differential equation will allow us does come from a part of the wave equation. And this is called the Legendre equation. Except there's something I left out. And it's okay that I left that out because everybody starts with the Legendre equation. But this piece here also had theta in it. So I could have done all the same steps, but I could have said, all right, I want partial 1 over r squared sine theta, partial by partial theta of sine theta, partial f partial theta, plus 1 over r squared sine squared theta, partial squared f partial phi squared to equal a constant times f. And we already know what these solutions are. We already know that the solutions to this are e to the im phi. So this should be minus m squared f. And there should be a 1 over r squared in there. So if I do all of that and if I keep that in mind, and I also take what I had here, what I should really be getting is 1 over r squared times 1 minus x squared partial squared f partial x squared minus 2x partial f partial x minus m squared over 1 minus x squared, because 1 over sine squared is 1 over 1 minus x squared. And I could cancel the r squared. And what I'd be left with is something called the associated Legendre equation. But we're going to temporarily skip that because we're going to assume m equals 0. If m equals 0, then we have solutions that are symmetric about the z-axis. Right? We're going to assume solutions that are symmetric about the z-axis. Those are not all of the solutions, but we're going to start there. We're going to solve that equation when m equals 0, when everything is symmetric about the z-axis. We're going to get the Legendre polynomials. We're going to study their properties. Then later this week, we will say, okay, now let's consider the case where m is not 0. We have an equation that's similar but more complicated. The solutions to that similar but more complicated equation will be similar to but more complicated than the Legendre polynomials. And when we're done with all of that, we're going to understand everything there is to understand about how solutions to the wave equation in spherical coordinates depend on angles. Okay? So for now, we're going to focus on this. And last week we talked about solving these equations, solving differential equations like this using power series. And we started doing some things with power series where we had to worry about whether any of these coefficients were 0, whether this coefficient was 0. And if that coefficient of the second derivative is 0, then we could have a problem. We could have a singularity wherever it's 0. But this coefficient, the coefficient of the second derivative equals 0 if x is plus or minus 1. All right, so we might have problems when we might, I didn't say we will definitely, we might have problems when x equals plus or minus 1. We have no problem when x equals 0. So all that stuff I was saying last time about singularities, we're going to let that slide. And we'll come back to that next week when we get to the Bessel equation and we can't ignore singularities. But for now, everything I started developing last week, we're just going to let it slide. So f is the sum from n equals 0 to infinity of a sub n x to the n. This is what we assume. Then the derivative of f with respect to x is the sum from n equals 0 to infinity of n a sub n x to the n minus 1. And the second derivative is the sum of n times n minus 1 times a sub n x to the n minus 2. All right, we're going to have to do a few tricks in order to get this into something that we can plug into our Legendre equation. First, our Legendre equation never has the first derivative by itself. Our Legendre equation has the first derivative of f multiplied by f, which means that x df dx is equal to the sum of n a sub n x to the n. And we always want to have things written in terms of the same powers so that we can equate like terms and make this easier to manipulate. And this kind of looks like n times 2 because I have doctor level handwriting. All right. Now we could write this in another way. If we said that n minus 2 equals m, then n is equal to m plus 2, and n minus 1 is m plus 1. So I could also write this as the sum from m equals 0 to infinity of m plus 2, m plus 1, a sub m plus 2, x to the m. You may be thinking, why is it that this index started from 0 when that index started from 0? Can anyone tell me why?
Because when
Go ahead.
never mind.
Technically, I should be starting from m equals negative 2, because if n is 0, then n minus 2 is negative 2. But what if I plug in negative 2 here? Negative 2 plus 2 is 0. So the term with negative 2 would be 0. I'm always allowed to leave 0 out when I'm adding. Then the term with m equals negative 1, which technically should be there. But negative 1 plus 1, 0. So if I just drop those terms, I don't normally get to say I don't feel like adding something up. If I say I don't feel like adding something, you know, that's me not doing my job. But I'm allowed to skip addition when the thing that I want to skip adding is 0. It's the one time that I'm allowed to not add things. Okay, so we've got most of what we need for the Legendre equation, because we've written the second derivative as a series. It starts from 0, goes to infinity, and has power equal to the index. We've written x times the first derivative. What we haven't done is written x times the second derivative, and that should be a partial x squared there. But the good news is that if I multiply x squared by this expression, I just get back an x to the n, whereas before I had n minus 2. So x squared d squared f dx squared would be the sum from n equals 0 to infinity of n times n minus 1 times an times x to the n. And now that I've got all of this, we're ready to put the pieces together. We're ready to put together 1 minus x squared times the second derivative minus 2x times the first derivative minus c times f. All of that equals 0. That's one giant sum of, all right, we're changing back from m to n because that which we call our m would by any other name still be our index. All right, so we've got that minus an times n minus 1 times n minus 2n an, because remember, this was from just writing out the second derivative the usual way. This was from multiplying the second derivative by x squared. This is minus 2 x times the first derivative all of that is 0. Any questions? Okay. So let's do a few things. Let's note that every term has to be 0. Which means that n plus 2 times n plus 1, an plus 2 equals an times n minus 1 times n plus 2n plus c. Or an times, let's see, that's n squared minus n plus 2n plus c. So an plus 2 equals an times the following expression. N squared, sorry, n, this would be n squared plus n here. N squared plus n plus c over n plus 2 times n plus 1. All right, that's a series. And if all we want to do, if we were pure mathematicians at this point, we could say in some sense that we're done. Now, of course, a pure mathematician would never say that because they'd want to study the properties of these solutions. They'd say, hey, I just created a class of functions. Let's learn what properties this class of functions has. But still, in some formal sense, we could say that we're done. We have a recursion relation. If I am given A0, I could immediately find A2 because I just plug in n equals 0. Then find A4, A6, etc. If I were given A1, I could get A3, A5, A7, etc. Because, I just say, okay, well, somebody told me what A1 is. It was an initial condition. Somebody specified my initial conditions and said A1 equals whatever number. Then A1 plus 2 or A3 must equal that whatever number times 1 squared plus 1 plus my constant over 1 plus 2 times 1 plus 1. And then A5 or A3 plus 2 would be equal to A3 times 3 squared plus 3 plus my constant divided by 3 plus 2 and 3 plus 1. And I could just keep doing that. I have solutions to an equation. The mathematician is done in some sense. The physicist is not. Because our series would be, let's take the even solution. We'd have A0 plus A2x squared plus A4x to the 4th, etc. And we want to test for convergence. What is our radius of convergence? Well, the easiest test is the ratio test. So if I had an plus 2 x to the n plus 2 over an x to the n these are two consecutive terms, I'm going to get an plus 2 over an x squared. Okay, that's my ratio. Now we know that this must be less than 1 for convergence. There must be less than 1 at large n. Well, that ratio is up here. Now, if n gets really big, my numerator has an n squared plus some other stuff that's not as big as n squared. N squared plus etc. My denominator has an n squared plus etc. All right. And as n gets really big, the n squared dominates everything else. So I'm left with n squared over n squared, which goes to 1. So it looks to me like my ratio goes to x squared. Which is less than 1 if x squared is less than 1. Okay, any questions on that reasoning before we discuss the implications?
Are you just, when you did the ratio test and you wrote, or before you did the ratio test, you wrote down radius of convergence? Were you just looking to see if this series converged, or, I mean, what do you mean by radius?
I want to know for what range of x values does it converge?
Okay.
The radius of convergence is just the range of x values. How far can I go from x equals 0, the point I'm expanding about, before it blows up? We got a problem. This series blows up if x is equal to plus or minus 1, i.e. cos theta equals plus or minus 1, i.e. theta equals 0 or 180 degrees. So if we think about this as solving for a function on the surface of a sphere, because remember, this is the radial part of the wave equation. So our wave equation, our wave function, has something that depends on r multiplied by something that depends on theta and phi. Well, if we're ignoring r, if we say, I'm going to factor out my dependence on r right now, that's equivalent to say, I'm going to fix the value of r. And I'm just going to see what happens if I play with theta and phi. That's equivalent to studying this on the surface of a globe. Having a function that's fine everywhere except the poles, that's a bit of a problem. That means that we can't calculate the electric field at the North Pole. That means that we can't predict what the Earth's magnetic field would be at the North Pole. That would mean that we can't solve for a seismic wave at the North Pole. So if the Russians set off a nuclear test up in Siberia, and one of those seismic waves makes its way to the North Pole, then the seismic wave is just going to blow up with infinite energy and destroy the Earth. And we know that the Russians have set off nukes in Siberia, and we know that the world is still here. Based on the fact that 2020 happened, one could argue that the continued existence of the planet Earth is a mixed bag, but the fact remains the Earth is here. So clearly solutions to the wave equation in spherical coordinates do not blow up. Otherwise, anytime a seismic wave got near the North Pole, it would blow up. I mean, last night at 1:30 in the morning when I was working on lecture notes, I felt an earthquake. Yes, true story. And some tiny fraction of that energy might have made its way to Alaska. And yet the Earth is still here this morning. It didn't get sucked into a vortex of infinite energy. So any solution that blows up at the poles is unphysical. We have to reject those solutions. And now you're thinking, okay, the man just spent 20 minutes writing down a power series that he's going to throw in the trash. Well, I'm not going to throw the entire power series in the trash. I didn't waste all 20 of those minutes for you, just the part where I made the jokes about Siberia and blowing up the earth when a seismic wave hits the pole. All right. In fact, this series only blows up if it never ends. Okay. If A4 and A6 and A8 and A10 and all the even terms, A1 million, A2 million, A2 million and 2, A2 million and 4, all the way out, if all of those remain non-zero, we have a problem. What if for some AL, what if AL plus 2 equals 0? All right, because AL plus 2 is equal to AL times, what was that? N squared plus N plus C. So what if AL plus 2 is 0, but AL is not equal to 0? Okay, so AL is our last term in the series. C is, and actually this should have been, sorry. That should have been L squared plus L plus C over L plus 2, L plus 1. All right, then AL plus 2 is 0. And the same for AL plus 4. And AL plus 6, and all of the other even terms, all right? So we have a series that will terminate if our constant has one of these special values. If our constant just happens to be minus L times L plus 1, and that constant shows up with a minus sign in front of it, here. So minus the constant would be L times L plus 1. We have 1 minus x squared, d squared f dx squared, minus 2x df dx plus L times L plus 1 f equals 0. All right. Then we have something that terminates, and then we have a function that is well behaved at the poles. And we know experimentally that the Earth's magnetic field does not blow up at the North Pole or in Antarctica. We know that seismic waves do not blow up at the North Pole or in Antarctica. And so we know that these kinds of solutions must match with reality. These are the solutions to the wave equation that we should be looking for. Yes, Sebastian.
Just right above your boxed answer, it says if AL plus 2 is equal to 0, and then I can't read past that.
Ditto AL plus 4, AL plus 6. Yeah, that's not working.
What is ditto?
The same.
Okay.
Okay, so let's start constructing some of these. These are called the Legendre polynomials. an plus 2 equals an times n squared plus n minus L squared minus L over n plus 2 times n plus 1. So let's construct some of these. L equals 0. P0 equals 1. Okay, because we say that A0 equals 1. A2 is equal to 0 squared plus 0 minus 0 minus 0 over 0 plus 2 times 0 plus 1. All right, n equals 0, n plus 2 equals 2. L equals 1. P1 equals x. Blah. Because we say that A1 equals 1, then A1 plus 2 equals 1 squared plus 1 minus 1 times 1 plus 1 over 1 plus 2 times 1 plus 1. L equals 2. All right, we say the book actually uses a slightly different convention, and I'll get to why that is. But we're going to say A0 equals 1. So then A2 plus 0 equals A0 times 0 squared plus 0 minus 2 times 2 plus 1 over 0 plus 2 times 0 plus 1, which is negative 2 times 3 over 2 times 1 equals negative 3. But then A4, well, A4 has got to be 0 because A4 is A2 plus 2 equals A2 times 2 squared plus 2 minus 2 times 3 over 2 plus 2 times 2 plus 1. So 2 squared plus 2 is 6 minus 6, and there you go. So P2 is 1 minus 3x squared. And we could keep on constructing these. We could keep on generating polynomials like this, okay? The book, most writers actually do not generate them quite this way. They change the normalization. They multiply by some overall factor so that PL of 1 equals 1. Why? Ancient history. They just do. Okay. But we almost never write them as PL of x. We almost always write them as PL of cosine theta. So P0 of cosine theta is just 1. P1 of cosine theta is cosine theta. P2 of cosine theta is 1 minus 3 cos squared theta. And then I should really be putting in, multiplying by some overall constants. This should be over -2. That way, if I plug in 1 for my input to the function, 1 minus 3 times 1 would be -2, divided by -2 would be 1. I've been throwing a lot at you. Someone must have a question.
Professor, I'm sorry.
Switch to Mathematica and play with these. So if I go into Mathematica, this is a file that's based on something I got from Wolfram. I made a few modifications to it. What we're plotting here is we're plotting what the intensity would be if we actually, like what would the value be for different values of theta? And so the distance from the origin is the value of the polynomial. This might not look at all like it. You're trying to think, how do I relate that to a polynomial? Well, let's start by plotting. Here, I'll just do it this way. I'll add something to it. I'm going to add a second plot. Plot Legendre P of L x, x minus 1 to 1. And then I think I see the problem there that did not show up there. Okay. One more thing. Okay, so every time I change, here we've got a plot with L equals 2. Let's actually go much simpler. L equals 0, right? Our polynomial is a constant. Our distance from the origin is the same at all angles. We go to L equals 1. Our polynomial is a straight line. When theta equals 0, sorry, when cosine theta equals 0, theta is 90 degrees. The distance from the origin had better be 0. And indeed, you see that at the equator, this thing is pinched. You may be thinking, oh, that's not the equator. These are two separate spheres with equators. Remember, this is the plane theta equals 90 degrees. Here's the North Pole. Here's the South Pole. If we're up at a small angle from the axis is up here. We're very far from the origin. If we're 180 degrees down, again, we're here. Halfway between, there's a 0. Let's go to L equals 2. When L equals 2, all right, well, when cosine theta is -1 or 1, meaning theta is 0 or 90 degrees, then we have a very large distance from the origin. Our shape has a very large distance from the origin. We have zeros when cosine theta is, I don't know, a little more than a half. We have zeros when it's a little more than a half. And sure enough, if we look on here, you see how the curve goes into the origin when it's coming at an angle that's, around 50 something degrees, 60 degrees. And then as we get out to cosine theta equals 0, which means theta equals 90 degrees, in the equatorial plane, we're actually pretty far from the origin. Okay? And then as we go down, again, at this angle here, the angle that we're coming out at here, it goes to 0. And then if I increase again, now we've got a cubic polynomial with 3 zeros. And sure enough, those 3 zeros correspond to a node here at some angle above, away from the axis, but not in the equatorial plane. Then another one in the equatorial plane, and then another one coming down. Questions? Where do the P's come from? The P's are, the P is just the name, all right? They call it a Legendre polynomial because they do. In the last 4 minutes, I'm not gonna try to introduce a whole bunch of new ideas. I just want to fill one gap in what we've been discussing, which is that I was telling you before that the solution, that there must be 2 linearly independent solutions. Well, there are. I said to you, if our constant is equal to L times L plus 1, then AL is our last non-zero coefficient. That's not quite true. It's the last even non-zero coefficient, or the last odd. If L is 5, the 5th order term is the last odd term with a non-zero coefficient. If L equals 8, the 8th order term is the last even term with a non-zero coefficient. But if I said, oh no, say L equals 6, and A0 is 1, then A2, A4, A6 are non-zero, A8, A10, A12, etc. are 0. Well, what if I also said A1 is non-zero? I could always give it initial conditions so that that's true. There's no law forbidding me from doing it. The Department of Homeland Security won't knock down my door for saying L equals 6, but A1 is non-zero. Okay, I'm allowed to do that mathematically. If I do that, I'll get that A3 is non-zero, A5 is non-zero, A7 is non-zero, A9 is non-zero, A11 is non-zero, A14,605,000 is non-zero because 14,605,000 is an odd integer. All of those will be non-zero, okay? It's just that I'm getting a series that's well behaved except at the poles. So I would never want to use that solution. I never want to set things up with conditions where I need that solution. That solution doesn't correspond to anything physical. It corresponds to something very mathematical, but it doesn't correspond to anything physical. And I've actually done a lot of research projects that involve Legendre polynomials over the years. I've never had to use the other Legendre functions, those functions that blow up at the poles. I'm sure somebody somewhere has found an application for them. There's always somebody somewhere, but it's rare. Next week, when we get to Bessel functions, it's a different story. With Bessel functions, we often use the ones that blow up. And I'll show you why we use the ones that blow up, because we only use them in cases where we never actually plug in a value that would make them blow up. But believe it or not, we use them in fiber optic cables. Okay, we use them in the design of fiber optic cables. And you're saying, but light doesn't blow up in a fiber optic cable. Well, you're right, but outside that cylinder, but outside the cable, we have solutions that blow up on the axis, and we just never use those in cases where we're on axis. I'll explain what that means next week. What we're going to do Wednesday is we're going to talk about some more properties of these solutions. I'm going to show you some formulas that they obey. I won't derive all of those formulas. I'll derive a couple of them. The rest I'll show you. I'll derive the ones that have some relevance to things you're going to do in future classes. And then I'll show you the solutions to the associated Legendre equation when things depend on both theta and phi. And then on Friday, I'll have you do some activities where you test properties of these solutions in Mathematica. Have a good day.
Thank you, Dr. Small.
You're welcome.
Thanks, Dr. Small. See you soon.
You're welcome.
Hey, Dr. Small.
Yeah.
So I kind of figured like I did the worst on the last test, and I'm not like here to whine, but what I'm trying to ask basically is like, is there like a online resource or somewhere I can go to that can help me understand Fourier transforms? I don't want to like leave this class without having a good grasp on them, you know?
I'm trying to think. I don't have a good answer for a resource. I feel like Fourier transforms is one of those things that I've only learned in life by looking at many resources, practicing in many contexts. If I were you, I would look for a guide to Fourier transforms in some field or topic you want to work in. What do you want to do after college?
I know you kind of frown upon it, but astrophysics.
Okay.
But I mean, I'm also into like quantum and stuff, so I can definitely like it. I mean, I'm pretty sure those are applicable too. So,
well, okay. Everybody starts. Look, everybody says they want to be an astrophysicist. Everybody goes to that stage. The world is so much bigger than that. I mean, some people should do it, but if everybody did what they wanted to do when they were a small child, then everybody would either be, you know, a cop, a firefighter, a football player, or a cowboy. And, you know, the world would have a whole lot of people doing childish things, some of which would fit grossly with stereotypes that we're trying to move beyond. And so,
did you just call astrophysics childish?
no, but everybody, when they're a small child, everybody knows Stephen Hawking, okay? Everybody, you know, knows the things that get the press on TV. If everybody only did the kind of science that they see on TV, then we'd all either be astrophysicists or curing cancer. Other science that needs to be done.
You're right. I mean, I hope like in classical and, you know, the next level quantum, so some interest might peak because you're right. Like I still need to, you know, fish around some more, see what's out there.
If I were you, honestly, if you really want to do astrophysics, I would look at the Fourier transform section of a good book on image processing for astronomy.
Oh yeah. Okay.
And for quantum mechanics, let's see, what's a good quantum mechanics book that derives the Legendre polynomial, that deals with Fourier transforms? Fourier transforms are often covered rather poorly in quantum mechanics. It just sort of says, and here's how you make the transformation to momentum space.
So maybe like particle physics, you think that would be more? Because I mean, I honestly like I like most of physics except for but yeah.
I mean, Fourier transforms are a topic that's often well learned in the context of image processing and data analysis. So I went to an astronomical image processing book and read what they have to say about Fourier transforms.
Okay.
That's
Thank you.
Start.
And I don't, this might be like an office hours question, but like, do I still have a chance at an A? Like I don't expect you to remember like my grade, but
I mean, well, first of all, this conversation is being recorded, and while I don't have anything negative to say, you know, in general, details of grade should not be discussed in a recorded conversation. So let me pause the recording.